very same patch of sky in neutral hydrogen. There it is. Okay, it's all filled in, but there's a lot of interstellar medium between those stars. Now the way I've colored this is if you look to the side over here, it's bluish, and if you look to the side over there, it's golden. I've colored this on velocity, which means that the bluish gas represents blue shifted gas, and the warmish colored gas represents red shifted gas. So to those that are initiated, what you're looking at here is the rotation of our own Milky Way galaxy. So when you make an astronomy image, you don't have to give up the scientific content at all. And that's 21 centimeter data for the Canadian Galactic Plane Survey, which is very well processed, and everyone can go and get Canadian Galactic Plane Survey data and make beautiful images. This one has added to it the infrared data from the IRAS satellite, and that I've colored pink here, so that's the glowing dust. So there's a color coding here, and actually for each image will need a different kind of color coding. You can't do a kind of homogeneous color coding because it will make the images, well, each one has its own character and it needs its own color coding. You guys all know the science. Let's get into the visual literacy. Visual grammar includes techniques of composition, color harmony. The effect of using visual grammar is to create an image that engages the viewer and retains their attention. And I'm going to show you how it does this. It creates spatial depth, richness in color and detail, and it is a way of trying to communicate at least some of the content without the need of a legend. Okay, anybody here have any art experiments? Yay! Okay, Erica, what is it?
I did take art all the way through high school, and mother's a graphic designer, so she sort of passes on stuff to me.
Terrific. So you can add to this as we go along if you have something to add. It's great. And Harsha dances, so she has some idea about motion and composition. That's great. Okay, what are you, Blair?
I'm awkward.
I
don't do anything.
Okay, yeah, that was supposed to do that. Okay, here's the problem. This is Van Gogh's Starry, Starry Night, which is owned by the MoMA, Museum of Modern Art. And I'm still in the process of trying to get permission for use or in lectures. And because of that, I can't show you the real image. But you can just go and get on the Van Gogh Museum's two sites. For most people, what happens in most cultures is that your eye comes into the picture plane here in the bottom left-hand corner and goes straight out the top right-hand corner. Now, if your eye does that, the brain goes, been there, done that, won't look at it again. Okay? So what you want to do is trap the eye inside of the picture plane. Van Gogh does this in a great way. Here you come in, you hit this dark mass here, it slows you right down. Okay? Then you slowly get drawn up. And what I want you to notice here, there's many ways to guide your eye in this image, but I want you to notice this one in particular, right across there. That's a virtual diagonal. He hasn't drawn a diagonal line, but these swirls form a diagonal line there. So your eye comes in here, goes up to that diagonal, gets drawn by the brightness of that star and the other stars leading to it over here, falls down here again to this star, starts going around again, and finally circles around the church in this image. One, notice that church is not in the center of the image. If you stick your object in the center of the image, it's going to look like it's falling down when you hold it up on a vertical surface. Also, it's interpreted as a target or a bullseye, and it's static. And so your brain goes, boring. What you want it to be is dynamic. So you never put something dead center in an image. But also you see how you trapped your eye going around and around in the image. Let's do that for astronomy. A bunch of dead, white, old guys decided that we should have a convention where north is up and east is to the left because they're Grecian. And when you lay down on the ground and look up at the sky, you had a map of the sky. It didn't develop in the southern hemisphere, it would be different. So that means that this is the orientation we have in all of our catalogs. It looks flat. It looks just totally flat, like 2 eggs in a frying pan. All you have to do is rotate this image, and what do we have? Your eye comes in here. It's the virtual diagonal here. It's attracted to this star over here. It's attracted to that star. It's back at the beginning, and it stays inside the picture plane. So your eye is engaged and stays inside the picture plane. Something else happens. This arm here has a lot more detail. So as your eye stays engaged in the picture plane, this arm pops forward. When it pops forward, it creates spatial depth. The team of 7 or 8 scientists that did this wanted it oriented this way for public outreach. The Hubble Heritage team bought this. They stood behind me, we turned it upside down, did it like this, and became one of life's pictures of the year. Then everybody was happy. This one also is Van Gogh, Landscape with Snow, owned by the Guggenheim Museum. Please go to a Van Gogh Museum website and check it out. And here we have some nice diagonals again for the composition, keeping your eye in the picture plane. But what I'd like you to notice here is that the snow has got blue tones in it, and the mud in the foreground here. Isn't it nice how he drags your eye back to the beginning again, so you keep coming back? The mud is a warm color. Let's ask this question. If you were to do an astronomical object like this one, for you personally, which part is warm, hot in temperature, and which part is cool in temperature? Miranda.
Well, I would make the blue hot.
You would make the blue hot.
hot. Cool.
And most people see it as cool. Exactly. Because we just saw here, snow is blue and mud that's not as cold as snow is red, right? So our audience, exactly, is going to see this as the center, if it's a public audience, as cold, and this part here is hot. If you want to educate the audience that high energies are blue and hot, you could present them with this image. That's what the astronomers are doing. But another valid image would be one that could be read without a legend, without that caption, where you would somehow make this very hot looking and this very cool looking. And we actually tried to warm up this blue, so it's a turquoise blue instead of a cold ultramarine or something. In this image here, which ball looks like it's coming closer to you?
The red one?
Yeah, definitely. The red one looks either larger, like it's popping towards you, than the blue one. If we say that something's blue shifted, it's coming towards us, and it's red shifted, it's going away. So our color tables for velocity are opposite to how our brain is digesting that color and understanding that color. In a composition like this explains why you would want to ever use a composite composition instead of a chromatic composition. So remember, chromatic was where everything was ordered in the direction of the wavelength for the filters. Well, in this image right here, this gas would be red and would pop forward and sit in the same place as this star cluster. And we wanted it to go back and have the star cluster come forward so we would have a bit of depth in this image. So we decided to color that gas green, which is at least cooler than this pink here. Okay? And also notice the green and pink. We'll deal with that in a moment as well. So there's a very good reason for using the composite composition for your color assignment, and that's so that you can create three-dimensional spatial depth when you're creating nebular images.